at approximation algorithms. Okay, so last time we looked at NP-complete problems, and NP-complete problems are dealing with decision problems, but in reality, we really want to solve optimization problems. And then, of course, you can always turn an optimization problem into a decision problem. And if that decision problem is NP complete, then that optimization problem is called NP hard. Okay, so that's what this means. Oops. Okay, so this is NP hard. Change your color. So let me give you an example here. For instance, so one of the problem we are going to look at is called traveling salesman problem. I remember somebody asked it last time. So traveling salesman problem is the following problem. Now let me start a blackboard. How do I switch to blackboard here? Anybody knows that how do I switch to blackboard?
I think you have to hit done first to get out of there and then go back.
And then start, yeah, that's what I thought. Okay.
It literally just shows you what we're seeing on screen. So if you see it on the screen, we see it.
Okay. So okay, now you should see it, right?
Well, we've got a whiteboard now.
Right. So what whiteboard? So traveling salesman problem is the following problem. So you are given a weighted undirected graph G, and with a weight W. So what you are going to find is a Hamiltonian circuit or a path. So I want to find a path that starts from a node. So actually, it will be you find a circuit. So that means it starts from a node that goes through every other node exactly once, and ends at the starting node. So so you are given a graph G, right? So let's say this is a graph. Then you start from any node, then you go through every other node, and then you come back at the same node. So you get a circle, you get a circuit. Then of course we want with the minimum weight, total weight. Okay, so this is a optimization problem. It is not a decision problem. So how do I do a decision problem? So I can convert this into a decision problem into the following form. So we can say this is a decision. TSP will be the set of G. Now this is encoding of a graph G and K. Okay, so such that, okay, there is a, now let's give a name to this kind of path. This is called Hamiltonian circuit. So you start from a node, go through every other node exactly once and comes back. So that's called a Hamiltonian circuit. Okay, with weight at most K. Because you want to find the smallest Hamiltonian circuit, right? You want to find a Hamiltonian circuit with the smallest weight. So we convert it to a decision problem. You add one more parameter. So that is the bound. This is upper bound for your weight. So once we have this, then if this is solvable, okay, so if decision TSP is in P, is solvable in polynomial time, then TSP can be solved in polynomial time. Can be solved in polynomial time. And the reason is you can simply do a binary search on K, right? So you do a binary search. Oh, by the way, I should oops. I should put this as a unitary notion. Yeah, that should be all right. Okay, so we do a binary search on K. So you first ask, is G, let's say 1 or the smallest way, right? So we can say we let W be the smallest weight. So this is the weight. So this weight, so this is small w, this is capital W. So in your input. So then your Hamiltonian circuit, the weight of it, total weight cannot be smaller than, let's say you have n nodes, right? So cannot be smaller than the size of G times W. So what I want to know is whether this is in decision version of TSP. If it is, then I'm done because it cannot be smaller than this, right? So then I'm done. If not, of course, I can ask. Now we know that if we take the maximum, now let me use a. Maybe I should use a different. Okay, I'm just adding W min here, so this will be the smallest weight, and then likewise I can use W max. So I know this if you have a Hamiltonian circuit, then then its total weight cannot be more than this. But I don't know whether I do have a Hamiltonian circuit, but then I can ask. So I can ask. So this is a mean. This is a max. Okay. Now, if the answer is no, now if this answer is no, then you know that you don't have a Hamiltonian circuit at all in this graph. Then you can return no. If this answer is yes, then I do a binary search by asking, take the minimum, right? So G, so the weight will be max minus the middle point, take the minimum. And then I want to know whether this is true. If the answer is yes, then I will use this as a max and then repeat. If the answer is no, then I will change okay, so this is so if now we know that we asked this is because this answer is no, and this answer is yes. So then we ask this, right? So then we ask this. If otherwise, if this answer here is yes, then we're done. We found a Hamiltonian circuit with the smallest weight. Otherwise, if this answer is no, but this answer is no, then we can just simply say there isn't such Hamiltonian path, because if it does, then the total weight cannot be more than this. Okay, so that means now when we get down here, only when this is no, this is a yes, okay, then we get down to here. So if the answer is yes, it means then I can further make this smaller than this current number by making a half point between this case and the current case. That means now I just make this W max to this value. And if the answer is no, that means that my K would be, so the minimum weight would be from this point to this guy, right? To this one. So that means now I'm going to make this to be W min and repeat. So then until you find it, because binary search is a polynomial time. Well, basically it's just a log. It just log the capital, right? So this is the capital. So it takes this many times. So then you get a polynomial time algorithm for solving TSP. Okay, so the process I just described here has a name to it. So this is called Turing reduction. Or Turing reduction, just use, right now I'm using the decision version of TSP as an oracle. So I'm just making queries to this oracle, right? So for certain value of K, so if you are polynomial time solvable, then you can return an answer to me in polynomial time. Hence, I can solve TSP. All right, so that's how we can convert a optimization problem into a decision version, into a decision problem. And then we can use, then if this decision problem is NP complete, then I know the optimization problem is NP hard. Okay, so later, not later. we are not going to show that the decision version of TSP is, this is TSP, is NP complete, but I'm just going to say it. So the decision version of TSP is NP complete. So TSP is NP hard. So then, of course, if you have an NP hard optimization problem, then what do? Right? So, of course, we don't stop there. We cannot just say, oh, we cannot find a polynomial time algorithm. So I stop here. I gave up, right? So we don't do this. Instead, we're going to say, okay, can we find an approximation algorithm in polynomial time? So approximation in this case will be, I find a Hamiltonian circuit. Okay, and then its solution is not optimal, okay, but it's close to being optimal. Okay, in this case, it's a minimal, and so that is the idea. So now let's go back to this. So actually, we talk about approximation algorithms when we explained the maximum independence sets, maximum independence system, and how to find a maximum independence set. At that time, we talk about Matroid and Matroid. So remember that we look at the approximation algorithm comparing with the optimal solution. So we have an upper bound. So when that upper bound becomes 1, that it becomes a matroid. So that is really what we are interested in. So finding an approximation bound. So now let's see this slide here. To deal with NP hard problems while finding optimal solutions.
Sorry, if you're sharing or if you're working off the slides, we can't see them. We can just see the whiteboard still.
That's right. So I need to start sharing the screen. I'm sorry. Yeah. So the laptop is really better in this case. Okay, maybe I'll switch to laptop next.